Discussing today's topic is Faris Sheikh. Faris is a 3D printing specialist at Formlabs. He has helped Formlabs run over 60 live broadcasts around the world to educate over 21,000 engineers, manufacturers, dentists, and jewelers on how to successfully incorporate in-house 3D printing into their day-to-day workflows. Previously, Faris notably ran an online technology show on hardware and software products, totaling over 2 million global views. To learn more about our speaker, please visit the Bios widget. It's with great pleasure I now turn this special session over to Faris to begin. Faris, take it away.
Thank you, Chris. Thanks for that great introduction. I'm so happy that you guys are all able to today's live webinar. Please ask me questions throughout the presentation. There's a Q&A window, so type your questions away. I'll have dedicated time at the end. And we're going to have actually a special guest, not pictured here, that I asked on our engineering Q&A. So you'll have some real good moments to ask a real Formlabs engineer on camera. So quick thing I want to note is today's presentation was written with Andrew is a engineering and manufacturing expert in the industry. He's been consulting in this space for so long, from printing. So it was a pleasure to be able to build this presentation with him and write this information for you all. So let's kick it off. Let's do an introduction to desktop 3D printing and teach you guys some things. So the ultimate value in 3D printing is in the parts you make. 3D printing is a means to an end. It's really about the parts that we want to achieve at the end of the day. And to 3D print those parts, you need to factor really 3 different elements. The first is being able to speak the language of 3D printing, which are the basics of 3D printing technology and understanding how they work. The second is understanding the materials that are available on those technologies and being able to kind of select the proper material that's suited for you. And last is understanding some design rules for how you can optimize your design to be 3D printed and manufactured repeatedly through that technology. And in today's presentation, we're really going to focus and hone in on this first part here and teach you those fundamental concepts about different 3D technologies. This is actually episode 1 in a 3-part series, and we have 2 other episodes pre-recorded already that I will send you personally after this event later today via email. So yeah, let's kick it off with this episode. So in a brief agenda in this episode, we're first going to talk about how you can take your digital input and turn it into a file ready for printing. Then we're going to discuss the pros and cons of each different printing technology in today's presentation. And then we're going to talk about the dirty secret of 3D printing that no one really talks about, which is post-processing. And last, we'll talk about how maintenance that you need to consider and how to really scale with different 3D printing technologies. So before we jump into it, let's look at a couple examples. Here is an example of an FDM part here. This was a sensor mount in a weather station that Andrew worked on in his early days of 3D printing, like over several years ago. And this has been really fast prototyping. Here is an example of a drill prototype printed using an SLS printer. On here, an original robust prototype. And last, here is a actually real New Balance shoe that they released recently last year, part of their triple cell series. And the bottom half heel component of that shoe on the left-hand side there is actually 3D printed using an SLA printer. The question is, those are some great parts. It's pretty apparent that 3D printing has some really impactful applications, whether from prototyping and product development to all the way to end-use consumer parts. But how do you get there? How do you actually make those? So let's take a look at a universal aspect of all 3D printers. Since some of you might know about some of this if you're outsourcing 3D printing jobs, but a bunch of you guys are machining right now. 3D printers, at the end of the day, build parts layer by layer. Essentially what's happening is some sort of CAD or digital input, like 3D would be in SolidWorks or Onshape or even like an intraoral scan if you're in dental. That digital input is taken and converted into 2D slices and then recompiled during the print process. That's how a printer works. It takes that input and then builds it layer by layer. It's kind of like actually taking a loaf of bread and slicing it up. It doesn't really matter how thin or thick the slices are. What you can do is then take all those slices of the loaf of bread and then still put them together and get that form and that original part and object you had. So it's kind of like a 3D print in a way. So there's really 4 considerations to understand. I mentioned them earlier. We're going to cover each of them right now. Then we're going to kick it off with the first step, which is a CAD to print file. So I kind of just mentioned this already, but you have some sort of visual input today, whether it be a file you have or some sort of scan that you have. You want to get that fabricated. Do that to go from that digital input to that 3D printing process. You need some sort of software to translate that language in between. So your 3D printer knows how to build parts layer by layer. However, each printer has its own unique way in doing it. Some sort of software that can tell the printer how to do it. And so this varies from different printing technologies. So I'm going to show you a couple of screenshots. The first one here is a print preparation software for an SLA printer. And you can see that most of these softwares will have a slicing tool. So on the slider on the right-hand side, you can slice it by layer to see how each layer will be made, a cross-sectional geometry that will be shown. And other basic job info you'll see on the right-hand side, like the print time, the number of layers, the volume, some design considerations, etc. And selecting your printer and send the jobs. Yeah. Here's another one for an FDM printer. This is another software that people use. You can also select the material in the software. For FDM specifically, you can change the infill settings as well. Now, if you are actually coming from the world of machining, which it seems like a good portion of you all are today, you're probably familiar with the investment of time when it comes to tool path generation. It takes time to generate all those tool paths when it comes to subtractive technology. But the great thing about additive manufacturing is that all that happens automatically in the background with your print preparation software. It just magically occurs in the background in that software that takes care of it. So you don't have to go through that pain and that. All right. Cool. So what I wanted to mention is, depending on the printer technology, this is also pretty popular in the software. A lot of softwares will allow you to basically generate supports, and this is kind of a necessary component to certain 3D printers, and it will be able to generate supports as you can see here. And you can orient your part and kind of sometimes resize and reshape the part as well if needed last minute. So that's step number 1 of first consideration we mentioned. You can see the number of considerations on the top left corner here in the screen. So first consideration was the software that you need to translate so that your printer can know how to print. Now let's look at the second consideration, and that is the mechanism of the print process. So we're going to talk about each of these and how they work, how these printers work, then look at pros and cons, like advantages and disadvantages. So there's actually a ton of different 3D printing out there. Today, actually, a set of them. I'm going to focus on desktop 3D printers, desktop/benchtop 3D printers, and plastics primarily. So I'm not going to be talking about metal 3D printing or industrial big systems at all, just to clarify. And so when it comes to that, there's some categories. Let me show you. First is a category of material extrusion. Second is the category of vat polymerization. Third is the category of powder bed fusion. And fourth is a category of material jetting, and a couple others like direct energy deposition and sheet lamination. Now, in today's presentation, I've highlighted what we're going to focus on. Not all of them. Even when it comes to plastics, we're not going to focus on all of them for the sake of time and focus, and so that you can all comprehend everything in a good way. We're going to focus on FDM printers that falls under material extrusion, and on 2 of the most popular systems for vat polymerization, SLA and DLP. And then lastly, we're going to cover SLS as one of the popular systems for powder bed fusion. The rest of them we won't cover in today's presentation, so I just wanted to mention that. First technology we'll look at for a material extrusion 3D printing technology. This is known as FDM or FFF. So that stands for fused deposition modeling or fused filament fabrication. Here's a diagram courtesy of 3dhubs.com that beautifully shows this. At the center of the core of an FDM machine is basically two printer heads. In that middle, you can see a number 4. And what's happening is those two printer heads are depositing a hard thermoplastic material that's being fed from a spool, and the part number 1 in this diagram. So that's a spool of filament. It could be like PLA or ABS plastic, and it's being deposited by those printer heads. It's that once that filament goes in, it gets heated up to really hot temperatures, and it melts it, and then it kind of builds the part over time. I kind of equate this to a concept of like I don't know, you've probably used one of these in your life. And it's just like, those print heads are just like 2 hot glue guns, but they're really precisely moved by some motors in the X and Y direction. And that's kind of how it works. So you got 2 hot glue guns going down and building the part layer by layer. Cool. That's how FDM process works in a nutshell. Let's look at some advantages to this print process. The first is that there are a wide range of thermoplastics available with FDM machines. So you can work with a plastic like PEEK that's really high performance, all the way down to commodity plastics like polypropylene or ABS. Is working with some tried and tested thermoplastics you're probably familiar with. FDM generally produces strong parts. You can get some really strong, tough, and durable parts out of FDM machines. So those are the biggest advantages, I'd say, of FDM. Let's look at some disadvantages. Generally, FDM parts are going to be non-isotropic. Here's a diagram of kind of diving into this concept. So you can see some voids, some interfiber bonding regions, and then voids where layers don't fully adhere. Those are the red zones. And so if you think about the layers, you're depositing material in that print process. Sometimes those layers will not register properly. That's when you have void zones, and that is kind of common when it comes to the pure science behind FDM print processes. Because of that, actually, since you're not going to have proper layer registration all the time, your FDM parts are not generally watertight or airtight. So that's something you have to keep in mind. Another thing is that there are more significant layer lines in FDM parts if you compare them to the other technologies. This is especially kind of apparent in the early days of FDM in the 2010s. But as years have progressed, machines have been better at this and kind of reducing the layer lines. But this is still quite apparent. If you just grab a random FDM part, say from a $5,000 printer and compare it to a, let's say, $5,000 SLA printer, you will see noticeable difference in terms of lines for FDM parts. So that is difficult to produce parts. FDM parts features, textures, or very thin walls. So if you're printing, let's say, some sort of big, bulky part, you'll be probably fine. But if you had some thin fibs or thin fins or ribs, it would be kind of hard to get and achieve that quality you're looking for. So those are some pros and cons for FDM machines. Let's look at SLS machines and SLS printing. That stands for selective laser sintering. So as all 3D printing is, it's like FDM, you're printing a part layer by layer. In the FDM machines, we looked at kind of depositing a material. In SLS, actually, the way we start with the material is a powder material. So in the middle here, you can see this gray rectangular. That's actually thermoplastic nylon, powdered bed of nylon there. And what happens is a laser is shined and directed as, a step before that is that the powder is actually heated up by the machine. And then the laser starts to essentially center the powder and select the area, start to draw out the part in that cross section. And that happens layer by layer over time. And you can see, for example, what it looks like are petals that are being formed in this diagram over time. That's how selective laser sintering works. Let's look at pros and advantages to this process. Because you're actually sintering powder that's all stacked up on top of each other, all your geometries are going to be functionally self-supporting, which is amazing because you actually have basically material in that space throughout. So this means you can really stack up a lot of parts densely on top of each other. Compare this to FDM or SLA machines, you won't be able to tightly nest them and pack them as well. So that's a great benefit. Another thing is that with SLS machines, you're going to be able to print strong, durable, functional parts in well understood and time tested thermoplastic polymers like nylon, or as you might know it, PA12. And because of the material we're using to kind of during the print process, we have a lot of powder. So at the end of we're going to dive into this later in our post-processing section, but at the end of a print, you can take a lot of that used powder that comes out that wasn't sintered, and you can recycle a lot of it with new powder, and that can save you some costs over time. So there are some advantages to SLS machines. Let's look at some disadvantages. Disadvantages is really time investment sometimes, or not sometimes, the majority of the time, like this will happen. You'll have to be heating powder, and then also a cool down time I didn't mention. So once your part is done, once it's printed, there's a period of time you have to wait for that part to cool down because it was just, freshly sintered. Another thing is, since you're working with powder, powder is messy. And so this is a cleaning station for an SLS machine, and you'll have to kind of brush off all the excess powder, make sure it doesn't get in the air, you don't inhale that, and that's something you have to factor in and make sure powder doesn't get everywhere. Another thing is that this is the same materials chart I showed you earlier, but now we're zooming in on just a very small, limited section of materials that SLS machines can offer. The blue is like what you'll find the most common and most popular materials available in SLS machines. And what's highlighted in orange is possible, but is sometimes a little bit trickier to play with SLS machines. So those are pros and cons for SLS, and I hope that was helpful. If you have any questions, by the way, I just covered 2 technologies really quickly. Please type away questions right now in the chat. I will get to them at the end of this presentation. So we talked about 2 of the 4 main technologies we're going to cover today. Now let's jump into DLP. DLP stands for Digital Light Processing. Now this is going to be quite different than the other print process mechanisms I just explained to you all. DLP, the foundation of it all, is not like how FDM or SLS machines work. In previous examples, we were using some sort of hard material, whether it was a spool of filament or a powdered thermoplastic. In DLP, we're actually using liquid photopolymer resin. This is resin that is photoreactive, meaning that, resin that is photosensitive, meaning that when light hits it, it will react and it will cure. So at the base of this all, in number 8 in this diagram, is a resin tank. And that resin tank is full with a certain amount of liquid resin, and you have a source that is projecting basically an image on that resin tank. And then what's happening is you're having to move up, and you're building a part layer by layer up and over again. That's the fundamentals of DLP right there. You can almost think of it actually as like a movie projector. It just kind of projects light out and kind of with the drawing of an image, and then it cures that layer over time. So the advantages to this process. DLP speed is fast. It's kind of one of their big advantages that they have with this technology, because you're not actually, if you think about it, within FDM machines and SLS machines, we had some sort of drawing action that was occurring. So think of like as if we're using some sort of pencil and we're drawing out a layer. It's almost like what's occurring there. Whereas with DLP, you're kind of projecting it. It's like a flash at once. Another thing is that certain material options are enabled by the speed of DLP. This is a bit complicated and nuanced depending on the printer, but this is a possibility. And on top of that, DLP parts are actually isotropic because you're actually you have a strong chemical bond that is occurring by having liquid resin being photosensitive and reacting to light, which will actually create watertight and airtight parts for you, and that will give you some continuous surfaces, and you'll be able to channel different fluids and airflow if needed. So those are the pros for DLP printers. Let's look at some disadvantages. One disadvantage is the concept of voxel artifacts on printed parts. So I'm going to illustrate this too with an example on the left here. Let's say we're trying to print the cylinder, just a very basic model concept. And if you wanted to build that cylinder, like I said, you have to do it layer by layer. So you'll have to build each circular layer. So let's look closely at a circular layer that the DLP machine will try to print. That's how DLP works. It's like going back to math. a long time ago in math class, and you have graph paper. But if you're drawing, if the DLP machine is trying to draw basically a circle on this graph paper, that the circumference is actually going through several squares. It's not evenly cutting through all the squares. So when the DLP printer has to decide what parts to print, it's going to have to decide certain pixels to turn on and off in and outside of that circle. Now let's take a look at that. What that happens when a DLP printer decides to do that, it won't create proper circular shape. Actually, you can see here. Some of the boxes are turned on, some of them aren't. A paintbrush from Microsoft Paint back in the day. And the effect is essentially a voxel effect here, picture on the left, and a voxel side profile. You can see how it affects layers over time. It's almost like if you took a bunch of Lego bricks and you stacked them up on top of each other. And this is how it results in your parts. So square pixels will create voxel lines in your DLP parts. So this is what I would consider a disadvantage of DLP printing. The thing is, although DLP printers are pretty fast, it does not mean it's fast at creating parts. So what I mean by that is you could print your part fast, but you're not done by just printing your part. You have to process your part. And for many of the performance resins that DLP machines offer, there is a lengthy post-curing time for them. It can go up to 8 hours in some cases, like using this cure box and putting your part in to cure it. So there we go. We just covered 3 technologies, pros and cons. I'm going to jump into Q&A, see how you all are doing on questions here. We have a bunch of questions. Nice. I love it. You guys are really engaging here. Okay. Looks like someone wants this Formlabs t-shirt. Okay, I won't go into all the questions here yet. Please ask away questions. I just discussed 3 different printers. Let's jump into our final category of printers. That is SLA printing technology / LFS. SLA stands for stereolithography, and this last year, there was a new form of the same technology called low-force stereolithography that came out. So SLA printing is similar to DLP printing in the sense that you're taking a vat of liquid resin, you're polymerizing it. And so this is the vat polymerization group I mentioned earlier in the printing technologies. And so right here in this diagram, number 9, you can see a tank. And instead of a DLP printer, which is kind of projecting light and projecting light, you have a laser here that's kind of drawing that image and printing the part layer by layer. That's how it works. Better actually in this print process and for DLP and some others, you have something that's called like this high force event that occurs. Time you're trying to get to build that second layer or that third layer after the first one, you have to bring your part back to whatever the object or source of material is, and you have to kind of pull away that part from the tank or whatever surface there is. When that happens, there's a high force event, and in the case of SLA and DLP, you can kind of equate this to going to your kitchen, taking 2 glass plates, pouring something very viscous like honey in between them, and trying to separate them. It's not that easy. And what that does is it has some detrimental effects to your print over time. It can cause failures. It's not that great. And so last year, there's this new technology that came out called low-force stereolithography, where the bottom of the tank is a flexible film. And as you can see here, as the part is being lazed, as a layer is being lazed, the film naturally deflects off and upwards, and it creates a much lower force, meaning that there won't be a lot of stress and strain on the part as it's being printed and pulled up over and over again. Now let's discuss some advantages to SLA and LFS. We're going to primarily focus on LFS here when we talk about pros and cons. The first advantage is you get some really highly accurate and precise parts from stereolithography prints. A lot of people, I go to trade shows and I see this all the time. They pick up an SLA print and they're like, wow, was this injection molded? They compare it to injection molded parts. So let's look at this part in this diagram here. This is a real photo of a 3D printed part in SLA. Here's an FDM part, same exact geometry. There you go. So you can see that there's significantly more layer lines in an FDM part. Let's go back to an SLA part here. Difference there. Another thing is that you're actually able to achieve very fine detail in thin wall using stereolithography. Because of the laser spot size and the way the laser is being controlled, you don't actually have the voxel effects that you will get in DLP, and you actually can achieve that fine detail in thin walls that you need in your geometry. You look at this picture, I love it. It's a beautiful picture of a wing in contrast next to a US 1 cent penny. And so you can see that texture on that wing compared to Abraham Lincoln there. This is another great benefit of low force stereolithography. You get highly translucent parts, especially compared to standard SLA. So this is looking at even just more of the benefits of just LFS in general. On the left-hand side here is one of Formlabs' earlier printers called the Form 2. And you can see on the right-hand side of Form 3, which uses LFS, how much more translucent this pump housing part is on the right. And this occurs because of better layer registration. When you have low force stereolithography, you have lesser of a force as the part is being printed layer by layer. What happens is you have better layer registration. So yeah, let's say this is a layer right here. It stacks almost perfectly on top of the next layer. And then the more accurate the layer gets stacked on top of each other, the better that you're going to have light passing through those parts in that material. So that's a really nice benefit LFS offers. Another great thing is that there are a wide range of polymers available using stereolithography technology. So you're not limited to just thermoplastics. SLA generally offers so many different materials that you just have a numerous there, which is great to have. It's always great to have more options. Another benefit of SLA is just like with DLP, SLA uses airtight and watertight parts. You can see this coffee jug here from OXO. OXO actually was able to prototype this jug, the lids, and parts for this using SLA printing technology, and had airtight and watertight parts so that they could actually test hot fluid in between the parts in and out. And this is because SLA parts are highly isotropic. So, you can see in this diagram that there's a semi-reacted green state, and then there's actual polymerization reaction between the layers. Now, since parts are isotropic, you actually can stress and strain them from different angles and directions, and the part should behave the same way functionally. Very different from FDM part. Part is like, so if you strain it from one angle versus the other, it can kind of break or react differently, not as expected. It's almost looking at like taking a piece of wood and how a piece of wood can break or is more likely to break in one direction. But not the case with SLA parts. They are highly isotropic, and you don't have to worry about that. So we just covered all these pros and cons. Pros for advantages for SLA. Let's look at some disadvantages. If you look at the speed for SLA, it's kind of in the middle of the pack compared to other technologies. If we tried to print this 3-inch solid rod, a DLP machine could do this in about an hour. An SLA machine could do this in about 5 hours. And a FDM machine could do this in about 20 hours. Here's the data on kind of the speed if you compare 3 different part designs and across different technologies. Another disadvantage is that SLA parts are not true thermoplastics. The materials can be formulated to emulate or function like thermoplastics, but they're not going to be the true ones that you're used to. So if you're used to ABS, you can definitely find a material like Tough is the name of one SLA material to kind of get some of the properties you want, but they won't behave exactly as to what you're used to. Great, so those are the first 2 considerations I've taught you all today about 3D printing and desktop 3D printing. First was, a reminder, was being able to translate your digital file so that it's understood by a printer, and the second is understanding how those printers work. So hopefully you got some value out of print process mechanisms and pros and cons about them. The third consideration is, all right, your part has been made, whether it be an FDM machine or SLA machine or SLS or DLP, part is out the printer. What's next? Part isn't completely ready yet to be used. you will need to post-process your part. And this is the dirty secret of 3D printing most manufacturers don't talk about, because you don't really want to talk about it. It's laborious, and you want to kind of highlight the cool, fancy stuff about a printer. So let's look at this. It's everything you need to do post-print completion to get to your final part. So I'm going to quickly show you guys a graph here, and we're going to look at the overall speed. So we're going to factor in the time of a print on average for an average number of SLA printers, DLP printers, etc., and then start to think about the time for post-processing. So on average, if you look at a print time, DLP is the fastest. We kind of discussed that already. Runner-up is SLA, and then FDM and SLS on average on some sort of normal part geometry will be around the same time. Now, remember, this is highly dependent on part geometries in general. Let's look at the first step of post-processing. This only is applicable for SLA and DLP machines, because we're using that polymerization technology here. You have to clean your part and cure your part for engineering applications. And this is a kind of graph representation of that time input involved. So what do I mean by that? Part cleaning and part curing. Let's take a look. For SLA parts and for DLP parts, what happens is when it comes off the machine, you have a thin film of liquid resin that's still on your part. You don't want that. You really don't want to touch that. You should be wearing gloves during that process. And you need to clean that excess kind of resin off the part. And the way you can do that is usually rinsing it in isopropyl alcohol and or some other materials out there. And so here pictured is a machine where it will take an SLA part and dip it down automatically into a bucket of isopropyl alcohol, and it'll rinse that part out, and you can clean it and wash it. Once you've washed the part, generally you want to cure your parts, especially for many engineering applications. And this is almost like, think of it as like an oven and like baking a material in some ways. You're curing your parts to really achieve the mechanical properties that you want. And depending on different properties you're trying to achieve, for example, in this material here with clear, depending on the tensile modulus you're trying to get, you will cure it for a certain amount of time. And generally it will take somewhere between 15 to 30 minutes. Then there's curing for DLP machines. So same exact thing you have to do to cure DLP. But as I mentioned earlier, a curing for DLP machine will take a lot longer just because of the print process mechanism for DLP machine. So this could be up to 8, maybe even 10 hours in some cases. So hopefully you understand that first component of post-processing, which is part cleaning and curing time. That's only applicable to SLA and DLP though. Now let's look at the second and rest of the process for post-processing, which is support removal time. So that's highlighted here in red, and it's applicable for all printing technologies. You have to kind of remove this or clean up the part fully. And let's look at what that means. For SLS, that means you have a machine in a station. You'll have to do some sort of media blasting and brushing and really kind of taking away excess powder. For FDM machines, supports come in kind of 2 flavors. The first is the soluble support. So this is the support structures that will kind of dissolve in water. Or you'll actually have the second type of supports, which are printed in the same material as an FDM part, like the actual part you have. And then the supports will be made in the same material. You'll also have to break those away manually or using some sort of clippers or flush cutters. And that's a little bit more tricky to do. And third, with LFS, I'm highlighting low force stereolithography for a reason here, is once you have a lower force during the printing process, you, since there's not a high force when you're separating that part and printing that next layer every single time, you're actually able to print much smaller support touch points. So LFS offers light touch supports, and in this kind of video you can see here this huge part with the with this incredible support lattice structure. You can just rip it off in one go. That's like never been seen before when it comes to SLA in the past. And you can see this nice electronic housing component with those thin walls that are still intact once you remove them from these light touch supports. So here's a recap of what I just showed you all. And when it comes to post-processing, this is what is needed. You have the part cleaning and curing time and support removal time, and hopefully insight into that real time investment there. when it comes to post-processing. So let's look at the last consideration in 3D printing. That is maintenance and scalability. So what does it take to maintain your printer, and how easy is it to expand? When it comes to maintenance, it's important to understand what are rare components and how does that impact part quality. First is cleaning. So let's look at an FDM machine here and kind of what's needed for cleaning and maintenance. You'll have to probably clean your print head after each print. This is a hot print head. It's extruding plastic, and it'll get clogged over time. And there'll be many times you'll actually burn your fingers in this process. Our special guest is going to come on in a couple moments, who will actually offer some insight into this specifically. And you probably also have to clean UV lamps and clean print head wipers over time as well. So that maintenance is good to factor in. Then there's this concept of when it comes to maintenance, whether you have a technician, with a lot of industrial 3D printing systems out there that we didn't cover, you have a dedicated expert at maintenance. However, with a lot of the desktop printing technologies I explained to you all today, there's a self-serve model where you can kind of go in and maintain your printer. And that's one of the big reasons why 3D printing is becoming more common. It's a lot. So these are two different wear components that are common in FDM and SLA printers. Like I mentioned already, there's that kind of nozzle you have to replace and change over time because it'll get really clogged. On the right here is a laser module. Now, this is a housing for a laser module. And when it comes to SLA and DLP printers, you have to keep in mind that lasers will wear out over time. The quality will decrease, and that's going to be a natural kind of fact of this technology. I'm not going to go through each of the line items here, but I'll quickly show you these graphs if we screenshot them. This is comparing the total cost of ownership between the carbon 3D printers, which are DLP, and Formlabs printers, which are SLA/LFS. Real quickly, what I wanted to point out on this graph is that when you're investing in a DLP machine like carbon, there is actually a recurring cost. You're going to be almost like on a lease in a sense here, and you're going to have a recurring cost of $55,000. When you purchase a desktop printer like the Form 3, it's kind of a one-time payment. Obviously, there are recurring costs for materials in both examples, but the cost of ownership is staggeringly different. Here's the cost of adding that second material for both machines. Another example I want to mention is if you look at $40,000 worth of productivity, with the Stratasys machine that's about $250,000, you can purchase about only like 40% of that machine. Compare that to a 3D Systems machine that's about $200,000, you'll get about 20% of that machine. With that same $40,000, you can actually invest in a full carbon printer. But also with that 40K, you can invest in about 11 Form 3 printers. Not trying to say that one printer is necessarily better than the others, because different needs need to be met with different solutions. However, you're able to get a lot more kind of redundancy and overall reliability built in with risk over time here. Real quickly, let's look at a graph of investing in tens of thousands of dollars and how much part output you can get. So scaling with a lower cost printer will give you more progressive output over time. You put in 10,000, maybe you get like, this is a theoretical example, like 15 parts out of it. Whereas if you put in 100,000, you'll get 300 parts out of it. If you compare this for two different costs of printers, a $10,000 printer and a $50,000 printer, you're actually going to be at capacity with the $50,000 printer for a while. What I mean by that is you kind of have this step function. The more you need to print more parts, you're able to add more printers and scale progressively. But with a $50,000 printer, you'll have to wait for a while until you make another $50,000 investment. And that's when you'll get double that capacity that you probably wanted. It's very different than kind of incrementally increasing your capacity with a lower cost printer. But the thing is, realistic part demand doesn't look like a step function. It doesn't look like randomly you want to make 100 parts and then like randomly 6 months on the road, you're gonna have a magic 200 parts you need. That's not reality. So you can see the yellow bars here in terms of demand. And if you hone in on the sweet spot here, or sweet spot depending on which printer you have, if you have a $50,000 printer, your part demand exceeds the capacity for you. However, with the $10,000 printer, you're able to match it much more closely. And lastly, I'm going to conclude this by just giving you a teaser on material options. You'll want to factor in material options when thinking about 3D printing. So you want to ask yourself, what properties do you need today? Which ones tomorrow? And I want to remind you, at the end of the day, value in 3D printing is ultimately in the parts you make, not the printer necessarily. So it's really, if you don't get the right parts, it doesn't matter. And material is really important for that. Thanks for watching this webinar. So if you'd like to continue your education, you can watch our second episode of this series on how to select a 3D printing material. Please click on the link in the description below. Thanks.